Let's start. Our second lecture is invited Caroline. Most of you have suffered from GeoTASO retrieval. Here is an expert, the expert. If you have questions, you can ask Caroline. Caroline is staying all this week, so you can ask her. Okay. So first lecture was about the instrument. Second lecture we have gas retrieval. Third one will be airborne retrieval by Professor John Wong. Okay.
Thanks, John. Thanks for inviting me. I feel like I'm back in grad school. I was my PhD advisor in Toronto, and I have seen many presentations with gas signals in the for integrals. And Eric, actually, because I haven't seen since I graduated, was my office mate. So, yeah, I'm talking about an introduction to trace gas retrievals with GeoTASO. And some of you, this will probably be stuff that you know already. And some of you might be completely new, but hopefully strike some kind of balance where everybody can learn something. Maybe just as an initial, before I start, I should ask how many people have used GeoTASO data here? Okay, and how many people intend to use GeoTASO data? Some of you gave up. Well, hopefully it will be of interest. If not the actual spectra, then the results that other people are getting from the spectra. And you'll at least understand how they got there and what some of the issues might be, and how to quantify disturbances and that kind of thing. Okay, so this is just the introduction to what I'm going to talk about. I'll talk a little bit about the background. Probably a lot of you were at my talk on Thursday. I gave a 20-minute presentation just on kind of general results. And it'll be a little bit of repetition of that, but maybe with some more detail. I'll just speak briefly about level 0 to 1 decalibration, how we get from the raw data to a calibrated spectrum. And then I'll talk in more detail about the spectral fitting, including calibrations you can do with flight data, how to use the reference spectra from the instrument, which seems to be one of the main sources of questions that I get from people, fitting the slant column, and then finally calculating our mass factors for the instrument. So GeoTASO stands for Geostationary Trace Gas and Aerosol Sensor Optimization. It was funded by NASA under the Instrument Incubator Program as a test bed, the GeoTASO mission, which is now is a test bed for GEM and Tempo. And it has a fairly similar design to Tempo. So I'm on the Tempo group at Smithsonian. So that's one of the reasons I'm involved with this. And it measures with two 2D CCD array detectors, one in UV, and that's where we get ozone, formaldehyde, and SO2, hopefully, and one in visible, and that's where we can retrieve NO2, ozone in the Ship band glyoxal, which I have yet to successfully retrieve from GeoTASO, but if anyone has any luck, probably with Course IQ it'll be easier. Water vapor and aerosols. So the 2D CCD array detector makes measurement by having one dimension of the array being spectral, and one dimension is in the cross-track direction. And you get a 2D, so as the instrument moves along its flight path, it takes an image with the 2D CCD array detector looking right down, and you get 1,030 spectra across the track, and then it moves to the next point. I think the integration time is a quarter second. It moves to the next point in the track, takes another second. So here's a schematic of what it's doing. So it's field of view in the nadir. This is red. Here it has a 45-degree swap width. And that's divided into, in actual fact, 1,033 individual cross-track pixels. In fact, though, in reality, only about 970 are actually illuminated in the cross-track. So if you ever look at GeoTASO data, you'll find that there's no signal at the sides. And those are used for calibration. And in the same with the spectral dimension, there are dark pixels on the edges of the detector. And it also has a zenith view, so during the flight, the zenith port or the zenith view is commanded manually by the operator on the aircraft. And the instrument looks at an optical fiber to the top of the aircraft. So if you look at the data, you'll often see these chunks of time where there's no measurements being taken in the nadir. And those are either manually commanded dark spectra or manually commanded zenith spectra. And campaign to campaign, it's been quite different on how many zenith spectra are taken. You don't want to take zenith spectrum when you're actually flying over a power plant, so you have to wait for the right time. You don't want to take it when the aircraft is turning, because that can complicate things if your zenith is actually maybe at a sharp angle, and it complicates things for the people like us who analyze the data, and so the operators have generally been trying to take it when they're just flying over kind of a boring, clean area. So the native resolution of one of these little points is very fine. It's about 9 by 50 meters, depending on how fast the aircraft is flying and how high the aircraft is. And signal to noise is about 65 for NO2. That's way too low to retrieve accurate NO2, and same with formaldehyde. So what we have to do is co-add the spectra to reduce the noise. So for NO2, I've been co-adding to about 250 by 250 square meters, and I find that's just a value that the precision on the retrievals is higher than the measurement requirements that were set for the instrument was even built, and they're higher than the ARPA tempo, but I find that's a resolution that I think is probably more useful for people to look at the spatial distribution of NO2. Because if we have a lot of signal, the noise isn't really mattering as much anyway, and then people can further co-add if they want. For something like SO2, which is a weak absorber, you probably have to co-add a lot of spectra. This is a diagram of the optics, the main optics of the instrument. So the light comes in through a slit, a depolarizer assembly, and it's reflected and diffracted off of grating. And the beam splitter here splits the orders onto the visible CCD ray detector and the UV. There's also some filters in here, and the shutters in front of each of the CCD ray detectors. Those are what are used to take the dark current measurements. And so those can be manually closed by the operator. These are the campaigns that we've had so far. There's a couple of campaigns where I don't think anyone's actually analyzed the data yet. From the first test flights, there's an ocean color campaign, presumably ocean color people are looking at that. Discovery Cube, Texas and Colorado. I've been looking at it, and of course we have the data from Chorus Cubes here, which probably what most of you are interested in. It's also participating in a ozone campaign, or a campaign to look at ozone along Lake Michigan next year. And it's now kind of moving into, I guess, a science instrument. A lot of these it was part of these campaigns, but not officially like a core instrument or anything, which has been good for me because then I've had a long time to put data on the archive. But now it's sort of moving into science zone, where it's going to be participating in the study where there's very high levels of ozone on the shores around Lake Michigan, and it's not entirely clear why that is, so it's flying for that next year. Oops, oh no. Uh-oh. Okay, this is like universal language. So there's a paper that the PI from Ball Aerospace wrote in a proceedings journal that describes some of the details about the instrument. A lot of the trace gas retrievals and more details about the instrument in his first GeoTASO paper, which showed up in AMP this summer, so you can look in that for more details. I also have at the end of this presentation, and I guess most of you will be able to get somehow from me or Joan, a list of all the references in detail that I cite here, so you can look them up for more detail if you need it. Okay, in the presentation on Monday, I showed a lot of pictures and not very much text. Now I'm going to show a lot of text. I apologize in equations and not really pictures, but I've got 2 pictures to start, just to introduce basically what the electronic is, and then we're going to talk about how to get there. So this is an NO2 vertical column over downtown Houston in 2013 during one flight. So in this case, the aircraft was out here over the ocean. This is a zoom in of the center of the flight. And it flew in this direction, did a loop, came back down here, something like that. These were several sites that had ground-based measurements. And you can obviously see a lot of features, interesting features in this data. So the red is where there's a lot of NO2 in the column. And there's lots of oil refineries and petrochemical facilities and that kind of thing over here. And then this is just an area with a lot of traffic downtown. And if you look at the data flight to flight, it varies drastically during day-to-day, the patterns. This is NO2 over Denver. This slide showed up in a lot of presentations for GeoTASO. This is a raster scan, so instead of just flying with some of the interesting sites, they actually took the aircraft, like in the Corsair 2 campaign, and basically mapped the whole urban area by flying it in big loops that map the entire region. And this is about 3 hours in the morning, and then later in the day, 2-hour flight. And you can see NO2 levels just on the north side of Denver have changed drastically during that time. And there's like things you can pick out, individual towns, and I think is that a power plant there or something in that region?
Power plant industry north of downtown Denver.
Yeah, and then this is, I think, highways, public transportation. Is that what that is?
It could be the outflow too from
Yeah. Okay. Yeah.
the winds go west at night.
Yeah. Okay. So yeah, you can really see the effects of meteorology and then a few individual features here. And we have some data, I'm not showing just many days, 15 days or 14 days maybe, or 14 flights from this campaign. But we have some over oil and gas fields that are showing interesting NO2 features. And actually, there's almost too much data, and not enough people right now analyzing it. So there's lots of interesting things to look at in this data as well. So just to get everybody on the same page, this is old news to a lot of people, but level 0 data is raw spectra and detector counts, no geolocation. It's basically what's come directly out of the instrument. Level 1B is what most people will analyze when they look at spectra, and that's radiometrically calibrated and geolocated spectra. There's a level 1A somewhere in the middle of this. Usually not radiometrically calibrated, it has some kind of geolocation, I believe. And level 2 is the trace gas columns that we're trying to derive. I'll just say a few things about level 0 to 1B processing. Tom actually covered a bunch of this in his talk. And hopefully it's not the kind of thing you'll have to worry about much, but if you're like me, you'll find lots of weird things in the spectra as you analyze it, and you should tell people about it. So it can be fixed. And, but all aerospace has done the level 0 to 1B processing for the Texas and Colorado campaigns. NASA Goddard has done it for the Course AQ campaign, and they've done something completely different. They use IDL, they developed all their own calibration software. They have a long heritage in that, and Ball developed all their own separately. So it can be, the way the spectra are calibrated could be quite different. So these are the kind of things though that are done to the spectrum. So the dark current is removed from the dark current measurements that are made. And then the data could include corrections for various things like offset, crosstalk, smear, that you get reading out the CCD array detector. Out of band stray light, and you have, say, this has been an issue with GeoTASO. You have, say, red, the light from the red end ends up in a UV detector. Out of field stray light, where you have maybe the right wavelength, but it's not ending up on the right pixel. And then this data is converted to absolute radiance using a radiometric calibration that they sometimes take before, sometimes after the flight, and is geolocated. And this is a diagram of the array, or the CCD array, in case anyone's interested. So you can see this is this white region. There's 1,072 pixels. I can't remember which direction's which, but in the spectral dimension it's 1,072, in the spatial it's 1033. But only the center part is actually illuminated, and there's some dark pixels on the sides. There's also this matching readout array on the other half. And so there's, when you analyze the data, you'll find there's dark pixels. You won't use it to the very edges of the data that's provided. Now, when people analyze the data, they're going to probably, unless there's a couple people here retrieving clouds, so they might actually want the clouds. Most of us don't want the clouds. But I think there's actually a lot of interesting science probably in the clouds, because we can measure the clouds with a resolution of 950 meters, which you can't do for OMI or something. But the way I take out the clouds right now is very simple. I just use a cutoff radius. I say if it's over this amount for this particular flight, I'm just going to throw out that pixel, and I throw out the pixels just on that cutoff. But there are better ways to do it. So if you're interested, and that's something I have after I analyze terabits of data. Something that I intend to do is have better cloud removal, so you can do various things like using a ratio of different wavelengths. There's other ways to do it. This is a nice paper. It's looking at ground-based DOAS, max DOAS, but has different, I think 4 different techniques for cloud removal. So that's just one source. If anyone's interested in that, you could, if you're writing a PhD, you might actually want to do it better.
When you say radius cutoff, you mean higher value?
Yeah, I just say if the radius is, I don't have the scale here, but like these red ones are clouds, obviously, and I just say if this is the mean radius in the electromagnetic window during one swath of flight track. If it's over 2 times 10 to the 13, I just throw it out. But there's better ways to do it. So a few things to consider when you're looking at the spectra are that the instrument's been under the possession of 2 different groups. So it was designed by Ball Aerospace. The PI is Jim Lynch, and they did all the calibrations for Discover in Texas and Colorado. But in 2013, before the Ocean Color flight, it was transferred to NASA Goddard. The PI is Scott Jans. So it's different groups doing the calibrations, as I mentioned before. And the file format is also different in those files. And the instrument was also modified between each campaign. So in Discover AQ Texas in 2013, the first major campaign, they discovered there was a lot of stray light, less than 360 nanometers. And as Thomas has told us, there are ways to actually model that and remove it. The instrument's different now, so I'm not entirely sure all the different calibrations that were done that you could use to remove that stray light. But if people are really interested in Texas at UV wavelengths, then they would want to do a lot of work that I have not done yet. Before Discovery to Colorado, they put in a baffle to reduce the stray light. And then for Chorus AQ, they put on a new mirror coating. I believe these are all the changes. I've actually never seen the instrument, so I just sit at a computer. But I believe they put on a new mirror coating, and so it's, again, a different instrument for Korea. Not entirely, but it's probably a better instrument, actually. But there are different things to consider for all the campaigns. Also, as Thomas in the back will attest, each campaign has a different wavelength calibration. So he got the wrong one. And the slip function could also change. And so I thought it didn't change that much for Colorado, but they're remeasuring it for Chorus AQ to see how the new mirror coating or the new mirror affected the instrument. But it has a different wavelength calibration. Every time you move an instrument around, refocus it, whatever, it could be slightly different. So if you want the wavelength calibrations, be careful to use the right one. And you can ask me for the first 2 campaigns at least, for the different ones. These are some more details on the differences. So the Ball Aerospace is in blue, and the NASA ones, this Chorus AQ, are in red. So Ball Aerospace provides this data in the native resolution. So there are 1,033 cross-track pixels. And so you have to co-out if you're using the data. And NASA just gives it at, I guess they took my recommendation, I'm not sure, they provided it about 250 by 250 square meters. So they've already pre-co-added it for you, which is nice because you can get the data from an FTP and they don't have to send you a hard drive. Or you can actually get the Colorado data from an FTP, it just takes a long time. And you'll find as well, when you read the data, it's all in HDF5 format, when you read it, the Discovery AQ campaigns will have this kind of dimension for the radius. Each file is about 92 swaths along the track, 1033 across track, and 1072 sectorally. But then when the data is co-added by NASA, it's a lot smaller. They've also cut off the pixels that you can't use at the edges. So those aren't sent to you. The first gas wavelengths are not included in Ball's files. You need to get them from me or from Ball Aerospace. I suggest me. I'm not sure. They have different ones. I suggested something else, and then they changed them, but then not everybody got the message, and et cetera, et cetera. And NASA, though, actually puts in wavelength calibration, and they've done a better job in that their first guess, but they don't just have like one linear equation for the whole campaign. They actually have a cross-track dependent wavelength calibration. So that data is in the HDF file. The radiance units are different. Sometimes you won't care because you're just using maybe you're going to normalize your spectra anyway, but you might. And then if you're using absolute radius, they're different units. Ball does not provide latitude and longitude coordinates. These are really useful for plotting a box or field of view of an NO2 pixel, but NASA Goddard does. There are, however, a few things with Course IQ that you still have to watch. The data is not in any way final. Has geolocation errors, I think, that are maybe estimated at 1 to 2 kilometers. So they want to remeasure the slope function. There's a lot of work ongoing for Course IQ, so you can look at the data, but just be careful, there will be a new version of the spectrum. So before we get into too much, when did I start? Do you know what time I started? I'm wondering how long it's been.
You started 23.
23? Okay. So spectral fitting. Before I even get into the calibrations and everything, I just want to give a brief overview of what we're doing for spectral fitting. There's a lot of detail in these two papers here. These are both from our group at the SAO, and I used Gonzalez-Abad's syntax here, but this is the paper. The first one is a glyoxal OMI retrieval paper. The second one is formaldehyde OMI operational retrieval. And both of these papers have a lot of details on the spectral fitting, which is nice. So they're a good reference for how we're actually doing our spectral fits anyway, although you may choose to do yours in a slightly different way. So this is not a full-on DOAS retrieval. We're modeling the radiance spectrum here. We've got a reference, which we're going to talk about in greater detail later. The X's are things that we're retrieving. So this term here is Weir's law that Tom was talking about earlier. This is a slant column, this one up here. And this would be a cross-section, this alpha. The other parameters, you might call these alphas pseudo-cross-sections. So the trace gases are contained in this term, but we've got other things like a ring effect and undersampling. Undersampling, I'm not sure you need to worry about too much because the instrument has interchangeable slits, and some of the flights that were done early on, they were actually done to look at how undersampling affected the retrieval. So they put in narrow slits that caused us to have higher resolution spectra. It's a long story. So, but you may or may not need this. It's on the, I think it's kind of fun. Does anybody know? It's on the undersampling. Yeah. Okay. This is something called a common mode, which Kelly likes to use in retrievals, which is basically you do the retrieval, you get some kind of mean residual, and then you use that in the fit. And then when you get the fitting residuals out, then you have those get propagated into your retrieval fitting errors, and it gives a more accurate fitting error. And I come from Tom's, I don't know what Tom thinks about the common mode spectrum. I don't think it's very physical. We have lots of arguments about it. But most of these retrievals are using something like, are using a common mode, where they're using it to get improved fitting precision output that kind of gets styled in the end result. There's a scaling polynomial and baseline polynomials that we also fit, and those take into account low frequency things in the spectrum, like Rayleigh scattering and aerosols, and some low frequency calibration parameters that we haven't been able to accurately correct for. So now I'm just going to talk a bit about characterization using the flight data. GeoTASO, I think, is a pretty stable, well-designed instrument. That's my opinion. And compared to some instruments that we've looked at, it's not. You can almost just like fit a slip function from one flight, use it for all your flights, and be okay. And it doesn't. Thomas was showing us yesterday. It doesn't have huge differences. It does have dependency how the slip function changes across track, but the changes aren't huge. But this is something you might want to do when you're looking at the data initially. So what we always do with these data is we take spectra and we set a slip function parameter, then a wavelength shift initially to start. We also, because with the satellite data, when we fit an exo-atmospheric reference spectrum, we don't have any atmosphere to deal with. So it's a lot easier. With the aircraft, though, we have ozone in all the spectra. We can't get rid of it. So we fit pseudo-observers. We basically use the cross-sections of ozone at the same time to fit those as well. For the reference, though, we're using a high-resolution solar reference. So Kelly and an astronomer at our institute published a reference spectrum derived from ground-based data a few years ago. That's available on our website, but many of you may already use that already if you're analyzing satellite data. And there's lots of details in these 3 papers, and they're all listed at the end of the talk on how to do these calibrations. And this is some example of results. So GeoTASO has an interchangeable slit. It was designed, it has a slit holder, and you can put in any different size slit you want. And they all manufactured 4 slits of different sizes, and this was to test trade-offs between spectral resolution and signal to noise. And so that's why I have 4. There are 4 panels here. The top are UV slits, and the bottom are visible. And then this is the narrow slit, which was 26 micrometers wide. And so this is 4 slits. The points are measurements that were taken in the lab. So these are derived slit shapes during the Texas campaign for the 4 slit sizes that were flown during different flights, and then the corresponding observations. I ran out of time and didn't measure that one in the lab. Most of you won't have to worry about 4 slits. You're lucky. So this was determined to be the optimal split for the retrievers, and then they just basically went with 39 micrometers for the Colorado and Chorus AQ campaigns. So that's the one that's used now. So when you co-add the data, you have to do with co-adding. So the Discover AQ you'll have to co-add. Chorus AQ you won't have to co-add unless you're doing maybe something like SO2 or formaldehyde, and then maybe you want to. You can do two choices. You can co-add the slant columns after the retrieval. So you do a retrieval on 1,000 cross-track pixels. And I do this on a cluster. I like this option now. So when I published the data, I originally did it that way. But it takes a really long time. And there's also a few other issues with it that I won't get into, but you're probably better off co-adding the spectrum before the retrieval. That's a much faster analysis and probably better for various reasons. Okay. So another question I've got from a lot of people who start to use the data, okay, thanks, is what reference spectrum should I use? So there's a few choices. and this maybe isn't even exhaustive for this, but you can use the xenospectrum that we've looked at. You can use a nadir radiance reference, so you just take a clean area where you're looking down and derive a spectrum from that. You can do something more complicated, like a top of the atmosphere reference computed from nadir radiances. And this was done for the ACAM aircraft instrument, which was flown during Discovery Q in Maryland in 2011, and a postdoc from our group analyzed that data, and that reference again is at the end. And it would be nice if you could use an actual, real, high-resolution solar reference, but there's often many issues with that. First of all, this is taken from the ground. There's still probably some issues in this solar reference. And secondly, if you use a reference that doesn't have the same weird calibration stuff going on as your own instrument, then it can often be a mess. These are really the two options probably that most people would be interested in. One of these two. So using a xenospectrum has, I think, can take a poll of GeoTASO users that I might say that from people I've talked to, this is the single thing with the data that has caused the most confusion. So the instrument looks up through the fiber. The fiber feeds light only onto the central part of the detector. So you don't have this 45-degree angle with 1,000 or 970 pixels of light in the spatial, in the spectral dimension. It's only feeding it into the center of the array. So this is a plot showing wavelength. This is a xenospectrum, and I've taken one scan, a long track scan, and looked at it in the spectral dimension. And this is the radiance that's ending up on the detector array. And you see there's lots of light in the middle. So there's nothing on the edges except for this giant thing here, which is stray light. Don't use that. When I first looked at this, I thought, okay, that looks like something I should use. But it wasn't. And so, yeah, there's light here, so you can only really use the central crosstalk pixels from about 505 to 550, or maybe even a narrower band than that. Also, notice there's a lot of noise. This data is really noisy. There's not much light coming in. You need to co-add many, many spectra. So what I did for Texas was I took 30,000 xenospectra or something and co-added them together. So, and I took several sequences. So it looks up, takes xenospectra, looks back down. 20 minutes later, it looks up again. 20 minutes later, it looks up again. I take basically all the spectra within maybe 20 minutes of an observation, co-add those into the xenospectrum. And I also would normalize it before I did that. Also, another thing to be careful with is it's not radiometrically calibrated from Texas to Colorado. It didn't do that. Using a radius reference may be a good choice for a lot of people. And preferably a cross-track radius reference. And the pros of this, so that it reduces the cross-track striping. You get with these CCD array detectors, you often get cross-track striping. You see it in like OMI data, a whole lot of instruments that make these kind of measurements. It improves the fitting residuals and the fallout fitting error estimates that would come out in your retrieval, and helps reduce any effects of the changing calibration across track. And I found that, say, with formaldehyde, it's really the only way to get good data. But the cons of it, you have to find a clean region. That's harder for Course AQ. In Colorado, there's actually quite a lot of clean regions outside of Denver, so it's not a big deal. But here, it will be maybe for Course AQ more so. And maybe, I haven't really tested all this, but there's not NO2 in the stratosphere, so this is a good way for us to remove NO2 from the stratosphere, if I haven't seen it. But I'm not sure what information loss there might be in that case. This just showed some calibration differences while looking at the instruments across track. This is a wavelength shift. Thomas showed some stuff like this yesterday. These are wavelength shifts that I retrieve during the calibration, and you can see in the visible, there's a big wavelength shift on one side of the array, and it has this very consistent pattern. And the UV, there's a lot more coads here, so I was retrieving formaldehyde. And that's kind of a similar one, although it's smaller, the sampling is different in the UV. That's some, I think, an expected effect, something to do with it. I can't remember what the effect is. It's similar to spectral smile in the spatial dimension or something. Anyway. So, spectral fitting. Don't put your notes on profile But for the trace gases, you'll do it usually a two-step procedure where you fit a slant column and then apply an air mass factor to get the vertical column, which is just slant column over air mass factor in. This again is the same thing I was showing before, but just with a few more points. So as well as this, all of these parameters that we fit, we also need to simultaneously fit something that represents a relative radiance to the reference, because as the instrument flies, usually some temperature changes during the flight, and the wavelength distribution of those patterns can shift. There's also, you can see this paper for more detail, what's called an I-naught effect that should be corrected for these spectra. And we also, in this polynomial, scaling polynomial, we set the zero order term to 1. Actually, we don't retrieve it because we have another parameter that we're retrieving up there. Those are just some details of our fitting. Okay, thanks. These are our examples of NO2 fits with simulated in red and observed in blue for optical depth. I showed this the other day. So for NO2, we're fitting in the window 420 to 465. And this is just an example. These are our different cross-sections, different molecules we fit, as well we fit our radiation spectrum for Raman scattering. Understand things we needed. These are different order polynomials that I determined by doing many tests. They're kind of a little bit higher than I would like usually for retrieval, but you'll probably want to find your own. And this wavelength shift again. The air mass factor calculations for the aircraft are also something that cause some confusion, and this maybe isn't too much math for a talk, but you can look at this later or look at the paper on GeoTASO. But the air mass factor is an integral basically of scattering weights that you calculate in one way, and a shape factor that you calculate independently. And these are scattering weights down here for a red is the zenith scattering weights, and blue is the nadir. And talk about the shape factor first. That's basically just the shape of the profile of the trace gas we're interested in. So you're taking the amount of NO2, for instance, at a given layer and dividing it by, you're basically normalizing it. So what's nice about AMS is that if you calculate the scattering weights, which are way more complicated than the shape factor, you can take any profile, apply it to the scattering weights, and get a new AMS. If you want to use a different modeling number to rerun all your radiative transfer costs, if you want to just say NO2 is all in the bottom 1 kilometer, and just use that single profile well mixed in the bottom 1 kilometer, you can do that. So where the fun starts is in the radiative transfer model to do the scattering weights, and these are the kind of inputs that we have to change each time. And I do a scene by scene calculation for every pixel, which I run on a cluster. It depends on the resolution you're looking at and how fast your computer is. If you want to get it that way, it's not really necessary. But we put geometry in, the ozone profile, which is very important for the penetration depth of the photons, which determines the AMF, the surface reflectance, aerosols, which I ignore right now, but can forever. And if I want to do, many of you probably use V-LIDAR, and in V-LIDAR, if I want to do nadir, I set something called upwelling flag true and downwelling flag false. And if I want to look at zenith AMF, I just change the flags. And you have to change the geometry as well if your viewing angle will be different. And these are the things that will come out of the radiative transfer model. So how do you actually apply that to your, it's not completely as simple as just dividing one thing by the other. What you're actually retrieving is a differential slant column between the S here is just your nadir slant column, the true nadir slant column, and the arrows I put are below the aircraft and above the aircraft. And the SR is the reference below and above the aircraft slant columns. So if you say S equals vertical times air mass factor, V times A, and you sub in all of these S's, and then you solve for a vertical column below the aircraft, which is probably what you want, then you get this equation. So if you had, say you were using a nadir reference and it was right at the exact same time as your nadir measurement, these two would almost cancel, these above the aircraft, these stratospheric, say, terms, except that you probably don't have the exact same air mass above the aircraft as you have. Well, yeah, so usually these terms are very tiny, but if you really want to do a good job, you might consider them. Some people who've done similar things have just said they cancel in a paper and ignore them, but it may or may not have some effect, those small terms. So hopefully some of you are not too scared off and either are already using GeoTASO data or want to. One of the main reasons that June actually invited me to the GEMS meeting was to help students and postdocs with GeoTASO data. So I'm available on Thursday and Friday if you want to have individual meetings or you have individual questions that I can't answer today. So just let me know. And also, at some point, somebody, maybe it was Jay Al-Sadi, nominated me as main science contact for GeoTASO for people who are interested in the data. So, and I'm totally happy to answer questions anytime you have any. And we're also happy to host people who want to come and visit us. We've had a couple of grad students from here who hopefully have learned a lot, but have been great as visitors. And if anyone wants to come, just let me know. We have lots of space. Public possibly not that great. I don't know. And you can also get the airborne retrievals. You don't just have to spectra. They're available on the NASA Discovery New Data Archive for Texas. You can get the Colorado spectra from a NASA FTP site. You just have to get a password from Jay Al-Sadi. And if you own the Course AQ spectra, those are available to the Course AQ science team. So you can contact Scott Jans or probably Jay for those. All right, that's it. Thanks.
Okay, so again, we can have a 10-minute break and we can ask questions to Carol. Questions? So when you say pseudo absorption,
Yeah.
do you mean like
Basically,
other gases